90% of the traffic was these peer-to-peer protocols. And they definitely have evolved from in the last 2 years and have gone more encrypted. So what you had as a more clear text protocol, as a protocol which you could identify, now stuff is getting encrypted. And the same is also the story with a lot of botnets. We used to see ICQ or IM connections to control botnet machines which the attackers had compromised. And now even the bots have started using encrypted communication. So what that means is, if you are a vendor looking at packets, and if you are trying to identify these attacks or these rogue applications, you need to be able to process these packets in real time and do intensive computations on them. So the next question you ask is there any other way in which you can still identify these rogue applications and be able to stop them? And PISA is the framework we are developing to identify that. And before I get into that, I will just give you an example of things like Kazaa. So what you see on the slide is you're having a Kazaa upload from one client to the other. Usually you notice that it can use any ports for uploading, file upload and downloads. But the request looks very much like an HTTP request. What you see is the file hash the Kazaa client is trying to download from its peer, and the HTTP request has headers which have Kazaa word embedded in them. So if I'm trying to detect it using a content-based signature, it is very easy for me to write a signature for this. I can look for the word Kazaa in the HTTP headers. Similar is kind of story with eDonkey too. This is another packet from an eDonkey client trying to download a file from another peer. And if you're not drunk and you kind of look at many of these packets for the file upload or downloads, you can figure out the pattern. And in this case, the pattern is very perceptible. You see all the file uploads begin with the command, which is the hex E3 character, and the packet length is encoded in the next 4 bytes. So the packet length here is 54, encoded 36 in little endian order.
And so, hi everybody. And so now we get to things like Skype. And this is a much newer protocol. And what we're seeing with Skype and these newer systems is that they're actively trying to avoid detection. They're generally not in clear text. They're generally not an easily dissectable protocol. Instead, they swap ports, they go to random ports, they encrypt all of their traffic. And as you can see, it looks essentially random. I mean, it looks like a send-mail configuration. Sort of bang your head on the keyboard, and that's what you get. So that's Go. Thank you. So now we've got the whole paradigm shift going on. And isn't that manager speak? I love that word. So we're going from content-based detection. Content-based detection is the classic. It's like cats. You can take the whole family to see it again and again. It's great. But it doesn't work when you're trying to identify encrypted traffic. So we're going to a statistical model. And what this does is this is going to look at the meta information that's available in addition to the content of the traffic. The content doesn't matter so much. We're looking at the things that you can see external to that. And Rohit's going to go over in a second the coordinates that are available external to the content. But so this is my favorite slide right here. That was pretty much me last night. Anybody else still drunk? No? Okay. But this is an important slide, comedy gold though it is, because it illustrates an important point. Through statistical analysis, you're only able to get a really good guess. This is never going to tell you 100% what you're looking at. Instead, you're getting a gut feeling. And we were actually concerned that it might be too gut or too feeling and not enough accuracy. But actually, with empirical studies, we've seen that we're getting about 95% accuracy on the identification. And I'm assuming with larger training data sets, we could actually get even higher than that. So these are the 10 coordinates that we're going over. All right? And imagine this is a 10-dimensional hypercube. It's great. We've got the average packet size to the client, average packet size to the server, the average inter-packet delay, how long subsequent packets, and then the standard deviation of those statistics. And then we also have the traffic difference between the server and client. So you can see how balanced the communication is, who's talking more, who's talking less, that sort of thing. And you want to go into the next one? And yeah, this is really interesting in that with these coordinates, we can differentiate between chatty protocols, Microsoft Exchange, NetBIOS, all that, because you're getting lots of very small packets very rapidly, or you're getting large packets more slowly. you're seeing things go in one direction. Things like HTTPS, it's encrypted. We don't know what's in there, but obviously there's one side sending a lot more traffic than the other. Now, if traffic is balanced in both directions, that's going to be something like peer-to-peer, Skype or Kazaa, one of the peer-to-peer things, because you're basically swapping traffic back and forth between two peers, hence the incredibly clever name. So, do we want to hit? Yes, and this is the 10th coordinate, and it's the coolest one, and so that's why Rohit gets to talk about it.
So far, the coordinates which Rob was talking about were more based on packet sizes and the interpacket delay, and their statistics like the average and the standard deviation. However, if you want to measure what the data is contained in these packets, you need to look at how random the data is. And for those people who attended a talk on Friday, there was a talk on using entropy to figure out which were the most interesting packets in a Wireshark packet. Like if you have a big, long Wireshark packet trace, and you are wanting to figure out which were the most interesting packets, you could use entropy. And we are using the concept in a similar manner to figure out what kind of protocol it is. Is it having a lot of the same characters repeat in the packet stream? Is it all text-based? Is it all random? And the entropy will measure us for the randomness in the data. So the function which people use for measuring entropy is the Shannon entropy, which I'll introduce in a few words. So if you have data set x1 through xn, and the probability of occurrence of each of those data is pxi, what you do is you compute the product of pxi with the logarithm of pxi, and that sum it over all the n data points, and that gives you a measure of randomness. To explain it a little more, let's say you had a packet trace, and all the packets were carrying the word A in them. So you have, for that particular packet trace, the probability of occurrence of letter A is 1. And so the entropy, which is probability of A into log of probability of A, is 0, because log of 1 is 0. And that makes intuitive sense, because what you're saying is entropy is 0, the data is really not random at all. Now, if you had another packet trace with only A's and B's in them, with A's and B's happening equally likely, the probability for A is half, probability of B is half, and you're getting an entropy value close to 1. So if you ask the question, what's the max possible entropy for me? The maximum possible entropy would be if the characters from hex 00 through hex FF all occur equally likely. So you have both the printable characters, you have all the non-printable characters, all of them are occurring with the same probability. So you have a total of 256 characters, and the same probability of occurrence of each is 1 over 256, which is 1 over 2 to the power of 8, and so you get the maximum entropy as 8 for the data sets we are looking at, for the characters on the wire. And in a sense, it's good. It's not increasing like the entropy of the universe keeps on increasing. So for our data, we collected a lot of Skype traffic. We collected traffic by talking to people in the same city, talking to people sitting across the cube. I have a lot of family in India and friends in India, so I make calls on Skype to them to make sure that we also have intercontinental Skype data, so to say, in the mix. And we also collected gigs and gigs of traffic in various environments. We went to people who were using mainly Solaris, and so we had a lot of NFS protocol data which runs over UDP. We also collected data from Microsoft environments, which was mainly UDP, which is the net BIOS. And we also collected data from the perimeter, which gave us things like UDP DNS traffic. And since we were studying Skype as an example of this framework first, we did concentrate on getting a lot of UDP traffic in our mix. The only caveat is we collected all the traffic in the broadband or speed environments. So if people are using dial-up, which I don't think anybody uses anymore, these statistics may not apply very well to them.
And so this is the experimental data portion. This is the part where I explained that, yes, we really did do all the work, and we really did collect all this traffic, and we actually did stuff with it. So we really did, I promise. So the experimental data, we wanted to see if we could differentiate. We picked a protocol And we wanted to see if we could differentiate this from all the other traffic that we collected. So we collected this massive amount of Skype traffic. I mean, talked to everybody we knew. And I mean, geeky as we are, we actually have a lot of friends. It was kind of cool. And so we collected all the coordinates across all these PCAPs. And then we took them and we sort of scaled them so across an interval of 0 to 2,000. And that made it scale invariant. That way, you know, you're comparing something like the Shannon entropy, which only has values of 0 to 8. That obviously give you a smaller dimension. So we scaled everything so a value of 8 would equal 2,000, a value of 0 is 0, so on and so forth. And that gave it a much nicer, broader range and a constant field. So if you want to go ahead and go to the next one. So this is the average packet client size. And what we're graphing here is the lower axis is packet number, because obviously things look different early on than later on. And then the vertical axis is the actual value graphed. And Skype is red, and all other traffic is blue. And so this is the average client packet size. This is traffic destined for the client, how big the packet is on average at that point. And as you can see, Skype falls into a very distinct band. It obviously doesn't want to send very large packets, and of course that makes sense being VoIP. It wants to get them out quickly and succinctly. So as you can see, it's very distinct that we've got, oh, and of course there's also video traffic we noticed was much higher. There's actually two distinct bands, if you can tell. The Skype video band is the top and the Skype voice band is the bottom. And so this was, we really got excited when we saw this. This was the first graph we did, because it was like, wow, we really can determine where Skype is. It's very distinct. So, and then this is the average server packet size. This is the traffic going the other direction. And server and client is just nomenclature at this point. You can actually, it's arbitrary for peer-to-peer stuff, but for HTTPS and things like that, we did actually differentiate. And as you can see, they fell roughly into the same two bands. The voice traffic up top, or the video traffic up top, and the voice traffic down on the bottom. And then we got the average client response delay. And this is the inter-packet delay. This is how rapid things are coming, the delay between subsequent packets. And as you can see, this is the video traffic up top. You can see there was actually a fairly long delay, but the voice traffic down at the bottom, very small. But once again, more importantly than that, is that Skype falls into a very distinct range. It's two very distinct lines, or two very distinct areas. It's very easy to determine where something falls. And then the average server packet delay, it's the same thing going the opposite direction. You'll note that it's once again falling into a very distinct range. It's very easy to spot where that is in the graph. And it's not just Skype, but we actually did this with several protocols. Skype is just the most interesting at this point, but all protocols tended to fall into roughly the same, roughly their own little area. And the favorite coordinate of all, Rohit and I fought about who was going to talk about Shannon entropy more. This is how random the traffic is. And as you can see, Skype is, can you see the little red dots up there? It's smack up against the top. It's very, very random. And that's true because, obviously, it's encrypted, and good encryption is supposed to be indistinguishable from perfectly random data, and it is. And also, the NetBSD random number generator, we tested it, also pretty good. All the other traffic is less random. Yeah, the stuff at the very bottom is actually really interesting. We were wondering what that was. We were looking at the PCAPs, and those were things like AAAA and XXXXX and 909090, and obviously, exploit buffer overflow traffic. And so we're actually looking at this as well as trying to find exploit traffic. This could be very valuable in that sort of situation as well, finding new exploits, finding new buffer overflows, that sort of thing. But the entropy is what really differentiates Skype in this case, or encrypted protocols in general. Also, as an interesting side note, that stuff right 1,000, those were mostly web pages and things like that. And that actually works out to be about the entropy of the English language. So just, for all you linguistics nerds out there, that's where it is. And finally, the traffic difference. Traffic difference is what tells us how much traffic is sent by one side versus the other. And as you can see, it's roughly linearly increasing with the voice traffic. The stuff up onto the upper left quadrant is all the video traffic. But the voice traffic is roughly linearly increasing, which makes sense because, one person talks and the other person talks and the other person talks. Obviously, this was not anything with my ex-girlfriend because generally all I say is, yes, dear, and I'm sorry. And I didn't know that, sorry. And so this was all conversations with people who let me talk. And it was great. And it really indicates that this is a very peer-to-peer application. It's not a simple server-client type of thing. And so it's really another useful coordinate in determining exactly what sort of protocol you're looking at. And so what's interesting is by about the 400th packet, the statistics really stabilize. It really becomes obvious that we're looking at different protocols. And 400 packets in Skype, depending on configuration, is about a second of talking, maybe even less. So that's really useful. We can tell within a second or two, that's Skype traffic. If you want to rate limit that, that's what you can do. So unless you're doing something very, very quick and just saying, hey, and then hanging up, doesn't do any good. But just to reiterate, you notice that the traffic fell into very distinct. That was the whole goal of the project, to see if we could actually say, oh, traffic in this band, this type of traffic in this band, this type of traffic. And what do you know, it works, which is good, because otherwise I would have stood up here and sort of said nothing. And so finally, we scaled those coordinates, like I said, and that's very important to remove. There's actually, it's actually what we do is calculate the Malhanobis distance, and that's important to do scale. It's important for that to be scale invariant. And so the average distance for Skype, 400th packet, is about when everything starts converging and making a lot more sense. And the samples for Skype all lie very close to each other, and that's great. That means that we really can use it to identify that particular type of traffic. So, there you go. And I'm going to pass it back to Rohit. He can actually talk about the results, which is the beautiful result of all of our work. So here he is.
So here again, I'm not showing all the PCAPs we used, but some PCAPs we left from the training data to see if this formalism can be used to predict the protocol. And here what we have is a NetBIOS protocol, and the PCAP is for the NetBIOS protocol, which we know. So as Rob talked about, it's a 10-dimensional space, and this PCAP basically is a point in that 10-dimensional space. And what we are computing actually is how far this point, which represents the PCAP, lies from the Skype cluster and lies from how far is it from all other traffic which we know of. And so as you can see, what is written output is the distance of this point from all other protocol clusters. And clearly, as you can see, that the best guess we can make, because this is nearest to the NetBIOS cluster. And if we were to make a second guess, if the distance was really not obvious, our next best case would have been the NTP traffic. Now, one question one may ask, why use this formalism for detecting protocols like NetBIOS, which are distinct with their port numbers? So 137 is a distinct port. We all know it's a NetBIOS traffic. But one application which we thought this could be used again is if tomorrow a new malware comes out and the malware starts using port 137 for its communications, and if we are observing these statistics on the wire, we can immediately figure out saying, hey, these packets which the malware, although it's port 137, really don't look like what NetBIOS traffic which we have trained with. So you can identify malicious, anomalous traffic using the same formalism. And again, this was a PCAP, which we did not use for our training set to figure out if the thing really worked. And as you can see, again, for this PCAP, which is a point in the 10-dimensional space, we computed its distance from all the other traffic which we had trained with. Best guessed, again, was Skype, which the packet trace was for, because the distance was least between this point, this PCAP, and the Skype center. So again, basically confirming to us that this kind of methodology will work for detecting traffic. And what we are planning to do in the future, so right now what we did was, although we scaled all the coordinates were scaled to a maximum of 2,000. So like one coordinate was not weighed much more over the other. So what we are planning to do is to do a weighted scaling of the coordinates. So we have a 10 tuple, a set of 10 values, which can act as weight to each of these scales. And what we would ideally like to do is, let's say you take Skype traffic, we want the Skype to lie in a really distinct region in that 10-dimensional space compared to any of the other protocols. And we can use scaling to do that. A real-life example of scaling would be, let's say you have a 2-dimensional plot and you have a circle in the 2-dimensional plot. If you start scaling the x-axis and stretching it out, basically the circle is going to turn into an ellipse. And if you do an asymptotic scaling, where you really stretch the x-axis far enough, you can collapse the circle onto a line at that point. And so basically, this weighted 10 tuple is going to exactly do the same as it's going to change the shape of the area where a particular protocol traffic lies. And the reason for doing that would be to better isolate that area from the rest of it. And if you think one step further, this 10-tuple is almost like your statistical signature now for that protocol. So if you are doing this live on wire, you keep collecting packets, you apply this 10-tuple weight to the packets and see where the minimum distance for the weighted distance from the other protocols you have seen. And if you do that, you can identify the protocol quite reliably. And this is actually, we are going to do that hopefully in the next couple of months, because with the amount of data we had, this idea of doing the 10-tuple weighting came to us only last week. And it takes a lot of time for the simulations to run, and so we don't have results right now to show for the weighted averages.
Is this header only, or is it good for the packet?
You're looking at the whole packet.
Well,
Yeah. I mean, it may work for some part of, for some coordinates, but not for the entropy.
right. Well, the entropy is actually looking at the data content. And something that we felt was really important about the entire system is we wanted to make sure it worked really well for real-time streaming packetized data. It's not just, I'm sorry? Oh, I'm sorry. The question was, does this look just at header, or does it look at the entire packet? And I'm sorry, yes? I'm sorry. Could you? I'm not quite sure what you're asking.
You're having to look at the encrypted part of it, not the, say you've got a protocol that uses separate network flows for signaling TCP.
Right.
Yes, yes.
Yeah. The question was just at UDP, are we looking if there's a protocol that uses multiple streams? Are we looking at both? We're looking at individual streams. But what's important is when we look at the encrypted data, we're not decrypting the data or anything like that. We're actually looking at simply the data content of the stream and calculating its entropy. And if the entropy is over a certain amount, we can assume that it's encrypted. If it's below a certain amount, we can't. We can assume that it's clear text, and so on and so forth.
And actually, we are also going to add another axis, so to say, to look at the derivative of entropy. So let's say you look at an SSH session or an HTTPS session. What happens is a lot of stuff is exchanged in clear text before till you exchange the real keys, and it's after that point the data gets encrypted. So if you're looking at the whole flow, what you will observe is the entropy kind of hangs around between 2 and 3 before the traffic goes encrypted, and then there's a sudden jump of entropy to 8 once the protocol gets encrypted. And so that could also be used to know when a particular protocol has gone from its signaling mode, initial session establishment mode, to now having encrypted data on the wire.
Do you find that using different algorithms changes?
He wanted to know if using different algorithms changes. Yeah, we actually picked these coordinates because they gave such very distinct results. There were other coordinates that we looked at and other distance calculation formulas that we looked at, and they gave much more cluttered results. And plus, we had to stop at 10 because Rohit was tired of me taking off my shoes to keep track of everything. But we're very pleased with how this works out, and this does give very, very strong, very definite, very distinct results for differing protocols. So, yeah, I'm sorry, back there. She wanted to know if we were looking at difference between attack data and normal traffic. Yeah, with that specifically, what we were looking at for the purposes of proof of concept, we were trying to detect Skype, but we also did detect a lot of attack traffic, and that was all the traffic with the really low entropy. Those were a lot of things like AAAA, 909090, things used as shellcode or NOP slides in exploit traffic. And so we thought, wow, look, we actually found some new stuff there. It was pretty cool, although it was sort of disturbing that we were finding it on local networks. But anyway.
And to be honest with you, we did not. When we used the training, we did not filter out the attack versus normal traffic. We trained it with whatever sample we got. And what happens usually is that if you have attack traffic which has a different coordinate for that sample, it's going to really lie out of band for that traffic. And so it will not affect the calculations much because that's one exception from hundreds of normal packets. So you are not going to deviate the average or deviate the standard deviation value that much.
Did you actually go back and find those packages?
Yeah, we looked at, the question was, do we actually go back and look at the packets that had the low entropy? And we did, and they really were shellcode. I mean, obviously in our network, we do a lot of testing, so that was most people just, testing exploits to our box and things like that. But yeah, we did actually go back and check, and that was really exploit code. We were pretty pleased. So, anybody else? Oh, I'm sorry, one more time.
Encrypted text looks slightly different than normal.
I'm sorry, say that. Well, so encrypted attacks versus, that's true. We did not take into account that the Skype traffic could be attack traffic, although all the traffic that we sent was generated by us, so we could guarantee it was non-attack. I'm sorry, in the back? He asked if it was different depending on time of day that it was collected. Yeah, it was actually very different. There was a lot more background static, obviously, during the day. We did try to collect it from all over the world, from Asia, taking into account time differences, it's day there, it's night here. And we did see some very distinct patterns there, and that's all part of the training set, so that the formalism does take care of that and does take that into account. So, anybody else? Anybody else? Yes, sir? Oh yeah, that was a lot of fun. The question was, did we have to come up with innovative solutions to crunch that much data? And yes, we did. It was actually pretty funny. We thought we could get away with just running some because the algorithm itself is simply calculating a specific statistical distance, and we thought, oh, that's not too bad. But once again, we had to calculate each coordinate cumulatively for every packet, because we don't want to know just what the average packet size is instantaneously. That every 400th packet is this size. We want to know what the average packet size is for all the packets up to this one, all the packets up to this one, all the packets up to this one, on and on and on. And we were taking about 5 or 10 minutes for a good-sized PCAP, and that was obviously going way too slow. So we sat down and did some really heavy optimization and came up with a really neat way, actually, to calculate cumulative entropy. Yeah, that was actually taking the most time. And it was really kind of funny, because I sat down and I just beat my head against the keyboard until I got it done. And first I thought I messed up, because it went from taking about 10 minutes per average size peak to taking about 30 seconds. And I figured I'd just mess something up, because generally when I touch anything it breaks. So I was really quite pleased that it wasn't broken. So we had to get pretty creative. Yeah. Oh, just one second.
In a couple of months we will release this code out so that you can take a look at it and train your sets too.
Yeah, still going through legal, can we release it, blah, blah, blah. So, I'm sorry, do you have a question? Yeah.
I'm not really from maybe a novice question, but has anyone tried to bypass this by doing standardized packets, that the packets are all timed equally, the packets are all the same size, and even though it's encrypted, so it's relatively useless, or I'm sorry, relatively random, if there is no data being sent to that time, continually sends an encrypted packet of just nothing data? Mm-hmm.
He wanted to know if anybody's tried to bypass this by specially crafting data. Nobody. This is still really just in-house. Nobody's trying to it just yet. And one of the goals is to try and find legitimate traffic that may just be subject to policy controls. So we're expecting that people using the normal Skype client or the normal Gizmo client or whatever are going to be using that normal protocol. When using this to detect attack traffic, we don't really know yet. We don't know if it's going to be easily bypassable, but I don't really think so. I think it's because it's testing so many factors, you'd have to really craft your traffic to get around it. So, Dustin? Oh. The question was, did we look at any malware or rootkit traffic? It was all serendipitous, actually. The initial goal was to try and find specific protocols, just as a protocol whole, like differentiate between HTTPS and Skype and SCP and all that. But some of the traffic that was just sort of serendipitously captured as part of the sample set was actually exploit traffic. And that was really interesting in that it stood out. So we knew that they were always the statistical outliers. So we could say, that's really interesting. This could also be used to detect exploits because they are so different from the normal traffic in that band. He wanted to know if these things actually showed up, and it does actually. For example, most of the data we tested was UDP because that was our initial theory, but it does actually show up. If you see something like that, it's going to look very different from everything else running on that port or with those statistics, and so it looks very different.
Like, I mean, many times you see malware which is on port 443 because it's open to the firewalls, and sometimes the malware in fact uses clear text on that port. So definitely, if you look at even the entropy going out on that port, you will notice clearly that it's out of a normal range because usually the traffic is encrypted, then entropy is higher. But if it's using just regular text traffic, you're going to see a difference in that.
Dustin? The question was, did we test it with routers rate limiting things along the path? Basically, we didn't do that as much as we probably should, but that's mainly because we didn't have control over every router between here and India on it. So my other box is your box, but anyway, no, we didn't test that as much, but that's a safe bet in that any routers interfering in the interim are going to skew everything anyway. So Skype would fail to work. I mean, if you have a router that's rate limiting Skype already, then it's not going to be Skype traffic anymore. It's going to sound like Verizon at that point. So,
and actually, to be honest, there is not any solution right now out there which can identify Skype. Because that's the reason Skype was chosen, because nobody can identify and rate limit Skype at this point of time.
Well, nobody but us, because we're that cool. So, yes, sir. Differing protocols for the same encryption. Can we identify those? Yes, because now all encrypted data, if it's good encryption, is going to have a very, very high entropy rate. But it's looking like we did have a lot of Cisco VPN traffic in the background, and that stood out very distinctly because with most VPN traffic, you're not getting a very constant stream. You're getting, I'm typing something and it sends something out, and then there's a long delay, and then something comes back. Lots of small traffic, lots of big traffic. There's a large mix. But so yeah, that does differentiate very well along the other 9 axes. So, anybody else? Oh, sorry. How big were the training sizes for each protocol? We had in total about 50, 60, 60 gigs of traffic total. Probably about between 5 and 10 gigs for each protocol. Was there any strategy for normal habits of traffic? Oh, overfeeding the training. Well, one of the goals with the training data was we wanted to get as close to normal traffic usage as possible. So we actually went into normal corporate networks, university networks, our corporate network, things like that, and got what we thought would be a reasonable sample of what day-to-day traffic looks like, and used that. We didn't doctor the sets at all, other than actually having a Skype call going on at that point. So, yes, sir. Right. Does SSL look different from SSH? It does. The encryption, we can't actually detect what encryption algorithm is being used because good encryption is supposed to look random, and they generally do. But SSH does look very, very different from, say, HTTPS. They both have a very high entropy score, but HTTPS has a traffic difference coordinate, a much larger average packet size, whereas things like SSH, very small packet sizes because they're sending keystrokes.
I was thinking about the nature of the conversation between client and service, fundamentally different.
Right.
So you can sort of identify things that the protocol needs.
Yes, that's exactly what the framework does. It's identifying each individual protocol by all these coordinates. Yes, sir.
Well, for the data sets between 0 and 256, yes. I mean, because you are looking at each, the frequency of each letter, and if you look at a uniform distribution for letters between 0, 0 and FF, a max value for the probability is 1 over 256 times 256 log of 1 over 256.
You do have the infinity of real numbers there. I mean, you can have 7.47357 2.1. Yeah, but the max is 8.0. Yes, sir?
Yeah, so HTTPS looks different from SSH or something like that. But what about comparing an interactive session over an SSL tunnel, like Telnet over SSL?
Looking at Telnet, okay, the question was looking at two interactive sessions like SSL or SSH and then Telnet over SSL. They do tend to look different. The saving grace there is that SSH tends to have more, like for example, Telnet, unless you're using a Nagel algorithm, SSH attempts to really randomize when it sends things out. So SSH will actually buffer things and then send it out. Telnet sends it out instantaneously. So you still get different packet sizes, different inter-packet delay, things like that. So it does differentiate itself on other axes. So, anybody else? Oh, sorry. Yes, sir. I am not at liberty to tell you, Senator. The question was, are we going to integrate this into tipping point? Yeah, maybe the next version, we don't know, but I can neither confirm nor deny that. So, yes, sir?
If you know the statistical analysis of signature keys, can you help any hackers get laid?
Can we help any hackers get laid? Well, it hadn't worked for me, so trust me, if I figure that out, I'll let you know.
Keep saying I'm sorry.
Yes, sir?
I was going to say, if you're planning on putting this into some kind of IDE, it have to be a smart solution on site, then you can have your signature start at a certain level for just general traffic, but as you're saying, if routers in the US situation would kind of change the traffic on each network. Very good reason. Wouldn't that have to be a smart one that would, say, adapt or allow some kind of variance from the signature to say this possible traffic? I mean, you said that it's a clear gut solution. It's the best feel. It's not exactly definite.
Well, although initially when we started this, we said it was a beer gut solution, but as we saw more results, right, I mean, it identified the traffic more or less more than 95% of the times correctly, because it depended on finally the distance between that particular ongoing packet trace and the clusters we had identified for other protocols. So we necessarily may not have to make that when we put it in the IPS, we probably don't need to make too many adjustments for the solution.
Yes, sir? The question was there a lower limit to the data set before we started getting meaningful results? There was. The lower limit was actually surprisingly small. When we started, we had about 5 gigs of traffic, and we were already getting pretty meaningful results. Once we hit about 10 or 15 gig, we started into the mid-90s in the identification. It was not as large as you would think, and I think that's telling in that, and that sort of validates the whole premise, which, whew, thank goodness for that. In that protocols tend to be very distinct in these realms. So,
I mean, as you saw that the Skype was being able to be identified within just 1 second of the conversation. So, we definitely did not require to get to the. I mean, although we have a lot of training samples, we could have done it with a fewer samples as well.
And the longest Skype conversation we had was about 20 minutes, I think, something like that. Yeah, it was pretty long. So, anybody else? Anybody? Oh, sorry. Yes, sir. This was continually updated. We would add new traffic on a daily basis and retrain, and we made sure to store a way that the traffic is never static. It's new data updates the old statistics as well. So it's not a log file system. It's a normal file system sort of analogy. So how do we know how that traffic is? That we intentionally looked for that kind of traffic, and we would make a Skype call, or we would do an SSH session, or something like that, and we would grab that traffic because that is one thing the system does need, is it does need a large training set to get the average to compare it with. So, anybody else? What kind of resources does it require? Are you talking? Yeah. To process a 100 meg circuit, I'm not really sure. The proof of concept is written in Python, which is great because the main file was pisa.py. It was hilarious. Comedy gold. But in Python, running against fairly large traffic, grabbed in real time and PCAPs, we were processing a 100 meg PCAP in about 10 seconds. And I would think that if we actually rewrote this in something other than Python, it would be considerably faster. So
were you just taking a slice of result?
we're real time updating it. It's every time we get a packet in, calculate the statistic set for the whole stream. So, yes, sir.
Yeah, actually, it depends on the kind of traffic you're looking at. I mean, obviously, in some cases, like if you're looking at chatty protocols, right, which are sending small packets quickly, you're going to have the average packet size there would probably play a more predominant role. And that's the reason for going to that weighted system, weighted scaling system, where you are able to weigh in one particular coordinate much better than the others, because that's exactly what we're going for, like trying to find the correct weight for the coordinates where a particular traffic is very well distinguished from the rest. So definitely we will have to work on that 10 tuple for each particular kind of traffic.
Anybody else? Anybody else?
Thank you.
Going once, going twice? Bueller? No? Okay.
Thank you.
So, thank you.
If somebody has a web farm with only one or only the other, what should be normal for them will be different from something like web services versus interactive humans with HTTPS traffic.
And that's actually the traffic data set is not just there you go. You guys are pretty folks. The traffic data set is not just collected locally for you. We actually are going to distribute training dictionaries.
But what I mean is that that might end up being harmful in the sense of if I have a deployment that I'm watching a whole bunch of web services traffic, which is, let's say, more symmetric volume